Welcome back. The 1944 Nobel Prize in Physics went to Isidor Rabi. He won for his resonance method for recording the magnetic properties of atomic nuclei. It's a large pile of scientific gobbledygook, but I want to say a few things before I explain all that. Up until this point, with the exception of the 1943 prize, a lot of what we talked about were things that led to the nuclear age and led to things that kind of finished out World War II. This is sort of newer technology now. We're getting into things that you'll find have a lot more applicability to our everyday lives. The other stuff does as well, but this is much more kind of still cutting edge modern engineering technology that you're finding dumps out of these prizes. This particular one from Isidor Rabi, he was a guy who was born in 1898 in what is now sort of modern day Poland, but then was part of Austria-Hungary, into a Jewish family who fled Europe and came to the United States when he was like a year old. And during World War II, he again was somebody who actually participated in the Manhattan Project. So he was around all that stuff, but his work, he wasn't necessarily one of the higher end guys there, but his work really kind of came after that. And after the war, he actually was very active in promoting peace and the limiting of nuclear weapons and that side of life. But he actually remained scientifically active up until the 1980s. And he actually played a large role in the formation of research labs that we still hear about today, like Brookhaven National Lab, CERN. He played a role in getting those off the ground. So what did he do that was so star-spangled important that we need to give him the Nobel Prize? Well, let's go take a look. What he discovered was a fundamental aspect of atomic behavior. So inside the nucleus of an atom, we find the proton and the neutron, right? Those are in there. Those are made up of different things called quarks. That wasn't known back then, but the proton and the neutron at this time was thought to be the smallest thing inside that nucleus. And as we learned in the 1943 prize, certain things inside there, in fact, both protons and neutrons can act like little magnets. They're small rotating magnets of a sort. And as a result, you can get them to align in a magnetic field. So what he did was he passed a molecular beam through a magnetic field and exposed them to intense radio waves at multiple frequencies, including microwaves. And by doing this, the direction of the rotation inside the molecule can actually be changed, but only in stages, which agrees with the quantum mechanical predictions that were coming out at this time. So as an atom returned back to their original state, what he found was it emitted this piece of this a certain specific frequency of electromagnetic radiation with very specific characteristic frequencies based on which nucleus it is. Now, all that's really cool and all that's really neat trivia, and it's neat in a lab, but who really cares? What are we going to do with it? Well, all kinds of stuff. Let's take a look. But without this fundamental understanding of nature, we wouldn't have things like the laser, the maser, which is the microwave version of a laser. We wouldn't have the atomic clock. And everybody goes, okay, great. Well, what's the atomic clock good for? Just so people can keep accurate time. Well, without the atomic clock, we don't have GPS. And without GPS, we all get lost everywhere we go. Come on, let's face it, be honest. You wouldn't make it across the street sometimes in a strange city without GPS. It's a fantastic thing, and it owes itself to the atomic clock. The atomic clock owes itself to the 1944 Nobel Prize in Physics. But wait, there's one more, and it's a big one. So the big one this year, without this understanding of the nature of what goes on inside the nucleus, we don't get magnetic resonance imaging. We don't have MRIs in hospitals. MRIs have probably saved more lives than anything else because you can create a detailed image of nearly every structure inside the human body. You know what it's supposed to look like. Now, what does it look like? What's wrong with it? You can tell if there's tumors. You can tell all sorts of things from an MRI that there was just no way to tell before its invention. And without this nuclear effect, this effect inside a nucleus, the MRI does not exist. So yeah, there's some of these prizes you may look at and go, well, that's neat and nifty inside a lab. But here we are, that's neat, that's nifty inside of the lab. But once you get it out of the lab and into the hands of engineers, now they have something to work with. And they've got the ability to create the laser, the maser, GPS, and MRI imagers, just to name a few. There's more I could come up with on this one because it's such a useful phenomena. But this particular one, I think not enough people know who this guy is. He's one of those guys that should be up there on the shelf with any scientist that's well known. But he kind of got overshadowed by a lot of the stuff from World War II and what was going on with the nuclear age. But fantastic series of things he came across. Please don't forget to click like and subscribe. It does help out with the algorithms. And we'll see you on the next prize. See you soon.